Again, hello everyone. So we are back here, I guess. So we are going to continue our session. So we are again briefly going to look at what we discussed in the last class and then quickly move on to our current lecture. So what have we been looking at in the last class? I believe we were trying to calculate the change in Gibbs energy, right? And that too for non-standard conditions. For non-standard conditions, yes. And so there are three aspects that we need to consider in that. And what are they? The composition, temperature, and pressure. So in the last class we talked about composition with respect to the reactants. So how do we go about calculating the relative variables or relevant variables when your activity of your component is not equal to 1, right? So today we are going to continue talking about the non-reactants. What will be the effect of the composition of the non-reactants or the concentration of the non-reactants on your relevant reaction or the relevant variables, and also the effects of temperature and pressure when they are not equal to either 25 degrees centigrade or 1 bar, right? So let's move on, I guess. So again, as we discussed earlier, if we have A plus B reacting to form C plus D, and let's say you also have E, F, G and H in your system. So how do reactions proceed, I guess, when molecule A collides with molecule B? That's when your reaction proceeds, right? So in general, the greater the concentration of your what do we say, molecules or reactants, pardon me, the greater the chances of your reaction going through. But in this case, let's say when we are talking about composition of other compounds, right, especially ionic compounds or charged species, and let's say your concentration of these charged species is relatively high, then they are going to have their own interactions, right, with the relevant reactants, right? Yes. And so the, let's say the probability of what do we say, A reacting or colliding with B would decrease. So in general, the higher the composition of the other compounds, right, you are going to have what do we say, a detrimental effect on your particular reaction, right? These are the composition just need not mean E reacting with A or F reacting with B, right? Just due to the charge itself and the relevant interactions due to the charge species on your reactants, you can have detrimental effects. So anyway, we are going to try to look at what it is that they are, right? So obviously we are going to have to calculate what do we say, a variable, and that's going to be equal to ionic strength, right? And so what will this give you an idea about? Let's say it's going to give you an idea about a measure of, I believe, effect of various charged species, various charged species on a relevant species. So more or less, what is the effect of the non-reactants? What is the effect of the non-reactants on your reaction or your reactants, right? So before we go further, in this case, obviously we can't use concentration, right? Concentration, again, as we said, we use the square brackets to look at that. So we say that we are going to look at a new term called activity. Maybe probably most of you have not yet come across it. So activity of your particular component. So we are going to look at what that is and how that's going to be equated to your concentration, let's say, right? So activity of any compound I would be equal to an activity coefficient, right, activity coefficient times the concentration or the dimensionless concentration. So to make that dimensionless, we are going to divide your concentration of the compound by the standard concentration. So let's look at what we just discussed. So we just defined activity is equal to the activity coefficient of that compound or component in that particular solution. We are going to come back to this, into the concentration of that particular component or compound by the standard concentration. So in general, activity is dimensionless, right? So concentration of the particular compound or component, you will have that, you know, and the standard concentration you are going to define it in such a way that, you know, this variable is going to be dimensionless. Again here we have a new term. What is this now? The activity coefficient. So this obviously depends upon, or let us say I am going to call that a function, I guess, obviously, of the type of solution. So it changes from one solution to the other. So thus you need to redefine whenever you know, you have a particular solution with different kinds of species. For example, let us say I am looking at A and B reacting, and I have C, D, E and F here. So I am concerned about what are the effects of C, D, E and F, you know, on this particular reaction here, let us say. And in another solution, let us say I have A reacting with B, and now let us say I have X, Y and Z compounds, let us say. So I am now concerned about what are the interactions between X, A, Y, B, YA, ZA, ZB and so on. So what I am trying to hammer home is that this activity coefficient varies from solution to the solution, right. So in general, again we need to talk about the four phases which we usually come across with respect to calculation of these activities. We will go further into greater detail with respect to activity coefficient later on. So first we are going to discuss activity in a bit more detail. So in general we look at four phases. What are they? We have the aqueous phase. So when something is dissolved in water, let us say, and then we have liquid phase. So for example, you have methanol, ethanol and so on in various proportions or such. Right, and then we also obviously come to the gaseous phase, and then again what else do we come across, I guess, the solid phase. So for all these three cases we need to define the standard concentration, I guess, right. So what is it going to be for the aqueous phase? It is going to be the molal concentration or molal units, I guess. Molal units, it is not similar to molar. Molar is something different, right. It is not the same as molal. There is going to be an error of around 3 or 4%, I believe. So what is molal, I guess? How do we define molal? Molal units you calculate by saying mole per kg. Molar units, mole per liter. In general, molar units, it is moles of your compound per kg of your aqueous solution or water in this or water, I guess, right. So molar units, and so obviously whenever you are calculating your activities, right. So activity of I equal to activity coefficient into Ci. So the Ci needs to be in molar units, and obviously C standard is going to be defined as, what do we say, C standard is equal to 1 in molar units, mole per kg, and thus you are going to have a dimensionless value here, right. So again moving on to the liquid phase, we are going to have a term called mole fraction. Fraction of moles of your compound to the total number of moles. So here we are going to have fraction of moles, right, or mole fraction is your relevant aspect or relevant what do we say, unit that you are going to look at here. And again gaseous phase, we are going to have partial pressure. We are going to have partial pressure, and that, you know, you can relate to that to again to what is it now, the mole fraction and so on, but again the units of Ci, you know, when you write down Ci by C standard, right, the units need to be in terms of mole fraction whenever you are looking at concentrations or reactions in the gaseous phase, right. And again coming back to the solid phase, we again look at mole fractions. Again mole fractions, number of moles of your solid by total number of moles of the other solids. So if it is only one solid, obviously, right, it is going to be a pure solid. If it is a pure solid, obviously your mole fraction is equal to going to be equal to 1, right. So these are aspects that you need to keep in mind, but in general in most of our lives, at least not lives, pardon me, at least in the engineering systems, we usually come across the aqueous phase. So keep in mind that you need to look at the molar concentration when you write that, and in the gaseous phase, which is something we again come across usually. So you will need to define your concentration in terms of the partial pressure. So this is the take home message here. So now we are going to move back to your activity coefficient, or how to calculate activity coefficient. So we are trying to calculate activity here, right, and for that we just looked at how to calculate this particular ratio. This C standard is equal to 1 for these different kinds of what do we say concentration units we just discussed, and Ci you need to obviously define that in molar units if it is aqueous phase, in mole fraction if it is liquid phase, in partial pressure if it is gaseous phase, again in mole fraction if it is a solid phase, right. So the next variable that we are going to have to look at is calculation of your activity coefficient. So moving on to the next slide. So activity coefficient, as we just discussed earlier, it is going to be dependent upon your ionic strength. So let us look at that particular value here. So ionic strength I guess here we have the relevant term 0.5 into summation of Mi into Zi square. Mi is the molality of your particular component, Zi is the charge of your on your component, right, the charge on your component, right, what is the charge, and here you can end up calculating the ionic strength. So once you calculate the ionic strength, there are different empirical equations. So we are going to look at that. Obviously you do not need to mug them up, right. So I think the most usually used law is the de Broglie limiting law, but keep in mind that this is only applicable when the ionic strength is less than 5 into 10 power minus 3 molar, right, or 5 millimolar. So let us look at what we have here. So we have log gamma I equal to minus A is a constant here, I guess, charge square into square root of I, right. So what do you see here? As ionic strength increases, right, I believe the activity coefficient decreases, yes, that is what you see here. And so what does this mean now? As your ionic strength increases, your activity, which is equal to your gamma I into Ci by C standard, that also decreases. So that is what you see now. So right, as the ionic strength, which will give you an idea about the various charge species in your particular solution, as they increase, the activity or the ability of your particular compound or component to react will decrease. So that is what you see here. So obviously it is limited only to ionic strength being less than 0.005 molar. So let us look at the other thresholds. So other threshold is with respect to I, or the ionic strength being less than 0.1 molar, right, and here we have the extended de Broglie. So again more or less another empirical equation here, you do not need to mug this up, they will be available in all your standard textbooks. So again we have ionic radius and those variables here, I am not going to go into that in greater detail. So depending on where your ionic strength is, you are going to use these relevant what do we say empirical equations. So again when ionic strength is less than 0.5 molar though, you have another empirical equation here, yes, and that is what you see here. And I believe lastly for neutral molecules too, you are going to have an effect, right, and that is what you see here, log gamma I equal to K, which is a constant I believe, and times the ionic strength here. What is the effect of ionic strength on the neutral molecules too? So that is what you see here. Again different what do you say thresholds with respect to ionic strength, right, and so once you calculate the ionic strength, you can choose which particular law to use and so on, right. Okay, let us move on. So looks like we are going to now move on to the aspect where the temperature is no more equal to 25 degrees centigrade. So until now we have discussed composition of both the reactants and the non-reactants, right, and we are done with those two aspects, and we are going to move on to the next aspect when temperature is no more equal to 25 degrees centigrade, right. You know, how do we calculate the relevant values, right, of the equilibrium coefficients or the delta G values. So I will start from a fresh page, right. So for temperature, I guess here we need to look at the original equation that we developed. So let us see what is K equal to, I guess. So I think let me go back to delta G is equal to delta G naught plus RT natural logarithm of Q. I am just trying to recall the relationship between K and delta G naught. And so if this system is at equilibrium, we said this is equal to 0, or delta G is obviously 0, delta G naught plus RT natural logarithm of K, and K is equal to Q at equilibrium. This is something we discussed in the previous class, right? So now we have K being equal to what now, or delta G naught equal to minus RT natural logarithm of K, or that translates to K equal to exponential of delta G naught minus delta G naught by RT, right? And here we will go back to the initial concept that we are aware of. Delta G naught is obviously equal to the change in enthalpy and change in entropy, the relevant equation here. So let us try to plug that in here. So the K equilibrium coefficient is equal to exponential of what now, minus delta H naught, right, plus T delta S naught by RT, yes, and that would be equal to exponential of, what is it please, delta S naught by R into exponential of minus delta H naught by RT. So this is an equation that we have here, right? So let us keep this in mind here. And so here we are going to proceed with one assumption that even if the temperature is not at the standard condition of 25 degrees centigrade, we can assume that, or we are assuming that delta S naught and delta H naught are not going to change, and this, you know, is in general, if you look at it, the error associated with such an assumption is relatively minimal, and we can go through with this assumption. And what we are assuming again, that delta S naught and delta H naught do not change even when we change the temperature, I guess. So how does this particular equation transform into? So K will be equal to a constant, or KT naught, let us say, equal to constant into exponential of minus delta H naught by RT, right. So that is what we have here. So let us take this onto the next page, okay, or on this page itself. I will try to work this out, please. And what we just have, we had, I believe, let me recall that K is equal to a constant, KT naught equal to a constant into exponential of minus delta H naught by RT, right. So now if I want to look at the change, right, when temperature is no more 25 degrees centigrade, right. So I can look at the ratio of K at temperature T, which is not at standard condition, by KT naught. So that is equal to constants cancel out, exponentials of what now, exponential of minus delta H naught by RT by exponential of minus delta H naught by RT naught, right. So what will that translate into now? Exponential of, so if I take out minus delta H naught by R as being common, so that is going to be 1 by T minus 1 by T naught, I believe, right. So that, if we simplify further, hopefully what do we end up with, I guess, KT by KT naught is equal to what now, exponential of minus delta H naught by R T naught minus T by TT naught, right, and this is what we have here, right. So now let us try to understand the system. So this is the final equation that we are looking at, right. So let us try to look at the case, what would happen, let us say we have an exothermic reaction, as in A goes to B plus heat, right. This is what you can, what do we say, represent the exothermic reaction as. So for this case, let us say that we are increasing the temperature. So let us say this can go through at the standard condition, and also at a temperature, let us say we are taking that to be 30 degrees or 40 degrees centigrade and so on. So what is the effect going to be on your delta G or your KT now. So take a moment, plug this in and look that up, I guess. So here we have two aspects to consider. So T naught minus T is now going to be a negative value, right, because we increase the temperature here, and we also know that it is an exothermic reaction. So delta H naught is also negative, right. So we are going to end up with KT by KT naught as being exponential of so on and the relevant terms. So it is going to decrease, right. So that is what you are going to see here. As you increase the temperature, compared to the standard conditions, you see that the KT is going to decrease compared to KT naught. So I guess how do you understand this system now, right? Let us again take a quick look at what we just had. So this is our equation, KT by KT naught equal to exponential of so on and so on. We looked at a specific example of exothermic reaction, A plus B going to heat, right, and we saw that if we put that in or plugged in the values, KT is going to be less than KT naught when T is greater than T naught, right. This is what we just observed. So let us try to apply that to what we see here though. So think of this now, let us say at standard condition A goes to B plus heat, and you increasing the temperature, what does that more or less translate into? It translates into you providing more of the product, right. Heat you can let us say approximate that or visualize that as a product now. So if you are increasing the heat content or the temperature, right, compared to the standard conditions, so what does that mean? You have more of your products initially now. So the reaction would not, for example, let us say if the reaction can go to this extent though, right. But now because you are increasing your temperature or your product here, the equilibrium is going to shift towards the left and it is not going to go to the previous value. So this let us say is KT naught and let us say this is KT. So I guess I am writing overwriting too much, let us again look this up. So here we said that KT will be greater than, less than KT naught when temperature is greater than T naught. What is K please? What are K? Equilibrium coefficients. T is at higher temperature than T naught, which is 25 degrees centigrade, and what the example we use though I guess is for a exothermic reaction. So what does that mean? So at T naught condition, let us say for example the equilibrium can proceed till this extent, let us say, right, and this is my KT naught, let us say. But because I am providing or increasing the temperature to T, or what does that translate into in this exothermic reaction? I am already providing some of the product here, let us say. So the reaction will not proceed to that particular extent, but it is going to shift, the equilibrium is going to shift to the left. So it is going to stop in layman's terms earlier. So this is for your purposes of understanding, and that is the Van Hoff equation, I guess. But obviously the corollary is when K or when T is less than T naught, what will that mean though? KT will be greater than KT naught, right. So what is going to happen here again? Let us look at this particular reaction. A goes to B plus heat. So now let us say you are in dearth of your products, right, the temperature is lesser. So instead of it going till KT naught, now your KT is going to move to the equilibrium is going to shift to the right, because now you have lesser temperature. So that is what it would translate into. So here now you are going to have KT greater than your KT naught and the equilibrium is going to shift to the right. So obviously if it is an endothermic reaction, you can do the relevant calculations and check accordingly, right. So we are done with composition and we are done with temperature. So now we are going to move on to pressure, I guess. So let me look up the relevant equation that I have here. So we are going to look at this particular equation, C2H6 plus 3.5 O2 goes to 2 CO2 plus 3 H2O, right. So in general here assume that all are gases, so everything is in the gaseous phase. And what are the moles here? I guess here Initially we had 1 plus 3.5 and that is equal to 4.5 moles, and we end up with 2 plus 3, that is equal to 5 moles, right. So what does that mean? It means that the volume has increased, right, or delta V is positive. Yes, in general any change in or increase in volume means PV, PV means it is work, right. So work needs to be done, yes, and from PV equal to nRT we know that 1 mole of any particular compound will occupy the same volume now, right. Anyway, keep that in mind that, so as the moles are increasing, see PV equal to nRT, we know that the volume is also going to increase, so the delta V is going to be positive. So rather than going through the same derivation again as similar to the KT by KT naught, here we can come up with Kp by Kp naught equal to exponential of minus delta Vr naught into P minus P naught by RT, right. So here we are trying to look at what is the effect on your equilibrium coefficient when you are changing the pressure. So the pressure at standard conditions is 1 bar, and let us say we are increasing the pressure now to 2 bars, let us say. So how is it going to change? So we can first, we will later on look at the equation, but first let us try to understand the system here, let us say. Here you are trying to change your volume by increasing it, right. So let us say now earlier you had 3.5 moles and now you are ending up with not 3.5, pardon me, 4.5 moles earlier, and now you are ending up with 5 moles now. So the volume is increasing, right. But let us say compared to the standard conditions you are increasing the pressure. So earlier it was 1 bar, now let us say it is 2 bars now. So as you know, the pressure would, increasing the pressure would restrict the change in this particular volume or increase in volume. So what does that mean though? So earlier let us say if your K P naught is to this extent, right, but because you are increasing the pressure, because P is greater than P naught, the reaction would not go to that particular extent, but the equilibrium is going to shift to the left, right. So you are going to have an equilibrium reach sooner compared to Kp naught. Hopefully that makes sense, right. So again now let us try to apply that to your equation and let us see if we can get to the same conclusion now. So here we have P minus P naught, P is greater than P naught, so that means this term is positive, right, and delta Vr naught, we know that delta V in this case, especially when the volume is, not especially when the volume is increasing, is positive. So when you end up increasing the pressure over the standard condition of 1 bar, we see that Kp ends up being less than Kp naught, and this is what we just discussed now, right. So when P is greater than P naught, and the case is that delta V is positive, right. So this is your take home message, right. So with that I am going to end today's session. So we will just have a quick review though. So what have we looked at thus far, and before what have we looked at today's class, I guess, right. We looked at, I believe, non-reactants. In the earlier class we looked at reactants, and today we looked at non-reactants, came across the term of activity is equal to activity coefficient into the dimensionless concentration. So for that we define different what do we say, units of concentration for different phases. And what were the phases, I guess? For aqueous phases we said the concentration units need to be molal, right. And for what next, liquid phase, let us say, we said the units had to be mole fraction, right, number of moles of your particular component by the total moles. And same case with the solid phase, we are again going to look at mole fraction, but for the gaseous phase we are going to look at the partial pressure, right. So what does that mean? Whenever you are calculating activities, let us say it is in gaseous phase, you need to use the partial pressures there, right. So again obviously I guess just for your understanding, let us say if it is a pure solid, you have only one solid, let us say, that precipitated out, what is the mole fraction going to be? It is going to be equal to 1, right. There is only a pure solid or only one solid now. So this is what we discussed, and then we looked at various empirical equations to calculate gamma I, right, and we saw that it's not proportional, I guess, inversely proportional to the ionic strength. As we increase the ionic strength, I guess the gamma I decreases, right, and that in effect means the activity of your compound decreases as the ionic strength decreases. What does this mean? So, when you have more of your non-reactants present, the ability of your compound to react decreases. So, if we look at this in the aqueous phase, what does this mean? So, when you had concentrated solutions, let us say concentrated solutions which are non-dilute. So, in these cases you need to be remarkably careful to be able to look at the activity of your compounds. But obviously, if these are dilute systems, when your ionic strength is very low, right, you do not need to look at what do we say activity coefficients or calculating activities. You can approximate activity as being equal to concentration, right. So, this is something we need to look at in mind, and then I believe we looked at the effect of temperature, effect of pressure on the equilibrium coefficients and so on, and then we looked at Kt by Kt naught and Kp by Kp naught. We looked at two examples when I guess what do we look at when T is greater than T naught for an exothermic reaction. We looked at what the effects are, and when P is greater than P naught, when delta V is positive, what are the effects. So, this is what we looked at in today's session, and I believe I am done for this session. Thank you.